All right. So, okay, let's continue. Now, once again, any questions about how we got the dual problem over there? So, once again, please pay attention to the fact that the number of variables in the primal problem is the same as number of constraints in the dual problem. And number of variables in the dual problem is the same as number of constraints in the primal problem. Okay, so there's a corresponding relationship between the two. Okay. So now let me ask you the following question. So remember, the way we obtained the dual problem was we started with the primal problem, which is this one right here. And we wanted to obtain an upper bound on the optimal value without knowing what the optimal value is, right? So that was our starting point. And that gave rise to this problem, okay? So what I'm going to do is the following. So suppose that now instead we started with this problem, okay? And since this is a minimization problem, now I'm interested in finding a lower bound on the optimal value, okay? So I don't know what the optimal value is, but I want to know if, that the optimal value cannot be smaller than a certain value, okay? So now I'm interested in finding a lower bound on the optimal value. So which means that now I'm going to start with this problem, and I'm going to try to find the corresponding dual problem. Okay? And the question is basically, will I sort of arrive at a different LP problem? Okay? So that's my question. So now I'm going to use this as my starting point. Okay? And I'm going to take the dual of this problem and see and try to see if there's a relationship between the primal problem at all. Okay? So that's actually a theorem. So this is theorem number 5, I think. Okay? The dual of the dual problem. The dual of the dual problem is equivalent to the primal problem. Well, basically what this says is the following. So if I use this as my starting problem, and if I take the dual of this problem, then I obtain precisely the primal problem, okay? And I'm going to show it by an example. So I'm going to start with this problem right here. Okay, so think of this as my starting problem. Okay. And what I want to do is, first of all, I want to turn this problem into a form that will look like this problem right here. Okay, so in other words, I want to make this problem a maximization problem with less than or equal to constraints. Okay. So how can I do that? Well, how can I change the objective function to a maximization problem? So multiply by -1, right? So that problem is equivalent to maximizing minus 10W1 minus 5W2. We discussed this before, right? So every minimization problem can be turned into maximization, vice versa. So instead of minimizing 10W1 plus 5W2, I can maximize minus 10W1 minus 5W2, right? Okay. Now, what about the constraints? Well, I have greater than or equal to constraints here. However, here I have less than or equal to constraints, right? So what I'm going to do is I'm going to turn these constraints into less than or equal to constraints. Okay? So how can I turn a greater than or equal to constraint into a less than or equal to constraint? So how can I change direction of this inequality? Just multiply by -1, right? So let's do that. And let's see what we have. So W1 minus W2 will be less than or equal to -5. Okay? I'll just do the same thing for the second one. Minus 3W1 plus 4W2 will be less than or equal to -2. And then minus W1 minus 2W2 is less than or equal to -1. And W1 and W2 are non-negative. So now this is a dual problem stated exactly in the primal form, right? So these two problems are the same, basically, right? And the thing is that, so in the new format, so that's exactly the same as this format right here, okay? So it's a maximization problem with less than or equal to constraints and non-negative variables. Well, the right-hand side values are negative, but I don't care, okay? In terms of the dual problem, I don't care about that, okay? So I have 3 constraints. So as a result, I'm going to use 3 multipliers, okay? And not surprisingly, I'm going to call my multipliers x1, x2, and x3, okay? And I'm going to now try to take the dual of this problem. And let's see what we have. So this is a maximization problem. The dual will be a minimization problem. Okay. What is the objective function of the dual of this problem? Minus 5 times x1, minus 2 times x2, minus 1 times x3, basically, right? So I have minus 5x1, minus 2x2, minus x3. Now, what are the constraints? Well, once again, I mean, this is really easy. So you're going to look at the first column. Okay? The first column is given by 1, minus 3, and minus 1. And you're going to multiply it with the corresponding x's. Okay? So we're going to have x1 times 1, minus 3x2, minus x3, basically. So x1 minus 3x2 minus x3. And the right-hand side value will be minus 10. And in between, I'm going to have greater than or equal to. Okay? So I'm just taking the inner product of the x vector with the first column of W1, W2. First column of the coefficient matrix, basically, right? 1, minus 3, and minus 1. And that's exactly this one right here. Then I'll just do the same thing for the second column. So minus x1 plus 4x2 minus x1 plus 4x2 minus 2x3 is greater than or equal to minus 5. Okay? And then x1, x2, and x3 will all be non-negative. So this is precisely the dual problem corresponding to that primal problem, right? Okay? Now let me compare this problem with the primal problem over there. Okay? Well, so if I look at the objective function, this is a minimization problem. So I have minus 5x1, minus 2x2, minus x3, right? Well, how can I turn it into a maximization problem? Just multiply the objective function by minus 1, and that exactly gives me this objective function right here. Okay? Let me look at the first constraints. x1 minus 3x2 minus x3 is less, greater than or equal to minus 10. Well, what happens if I multiply this by minus 1? I have minus x1 plus 3x2 plus x3 is less than or equal to 10 now, right? Well, that's exactly the same as this constraint here, okay? Similarly, if I take the second constraint multiplied by minus 1, I have x1 minus 4x2 plus 2x3 is less than or equal to 5, but that's exactly the same as, again, this constraint right here, okay? And all of my variables are non-negative, which means that the dual of the dual problem is equivalent to the primal problem, as we said, okay? So this problem is equivalent to the primal problem. So which means that basically, once we have an LP problem, and once we take its dual, and if we take the dual of the dual again, we just come back to the starting LP problem, okay? So we just go back and forth between these two problems, okay? So we never find another or different LP problem. So that's important. The other conclusion is the following. The role of the primal and dual are symmetric, basically, okay? So you can call this primal problem, and this is dual problem. Or alternatively, you can call this as the primal problem, then this will be the dual problem. Okay? So as a result, there's a nice symmetry between the two problems. So, whichever you call primal, the other one will be dual. And whichever you call dual, the other one will be primal, basically. Okay? So this theorem basically says that there's a perfect symmetry between the primal and dual problems in some sense. Okay? So, as a result, I mean, the role of primal and dual can interchange. Okay? Any questions? All right. So next what we're going to discuss is the following. So now so far we started with this type of an LP problem, and we arrived at the corresponding dual problem, right? But we know that in general there are LP problems which do not look like this one. In particular, there are LP problems in standard form. There are LP problems with greater than or equal to constraints and so on and so forth. And the question is, so if I have a different form LP problem, then how is the dual affected by that? Okay, so will I necessarily get the same dual problem, or will there be some differences in dual problem as well? Okay, so that's exactly what we're going to discuss next. So the topic is LP problems in different forms. I'm going to always keep this in mind, okay? So if I have an LP problem that looks like this one, I know that its dual actually looks like that one, okay? So suppose that I have an LP problem in standard form, okay? And what I'm interested in is the corresponding dual problem, okay? So my question is basically, if my LP problem is in this form, then how would the dual problem look like? Okay? Will it be the same as this one, or will it be different actually? Now to answer that question, so I know that if my LP problem is in that form, then I know what the dual problem looks like. Okay? So as a result, what I'm going to do is I'm going to take my problem and try to rewrite it in this form, basically. Okay? So essentially, instead of actually looking at this problem, I want to turn it into a problem that will look like that primal problem. Okay? And if I can do that, then I know that I can simply write down the dual problem. So if I look at the primal problem in that form, so all the all the constraints are inequality constraints, and in particular they are less than or equal to constraints. Whereas right here, I have an equality constraint. Okay? So now my question is the following. How can I turn this problem into an equivalent LP problem that will be in this form? Well, we already have equality constraints, right? So we don't need select variables. Let me repeat my question again. So what I want to do is I want to take this problem, okay, which is in standard form, and I want to rewrite this problem in such a way that it will actually look like this one. Okay, it will only have less than or equal to constraints, non-negative variables. And my question is, how can I do that? Well, so essentially, I don't want to change my problem, okay? So I don't want to destroy my problem, but what I want to do is I want to write it in an equivalent but different way, okay? So here comes the sort of the crucial question. How can I replace an equality by inequalities?
Smaller and bigger at the same time.
Exactly, exactly. So for example, if I have an equality constraint such as this one, x is equal to 3, then I can write this x is less than or equal to 3 and x is greater than or equal to 3, basically, right? So every equality constraint can be replaced by two inequality constraints. And that's exactly what I'm going to do. So I'm going to take this problem, and I'm going to write as follows. So I want to say maximize Cx subject to, first I'm going to say ax less than or equal to b. Okay? Then I'm going to say ax is greater than or equal to b. And it's not too hard to see that those two problems are the same, basically, right? Of course, I mean, I doubled the number of constraints, but I'm still looking at an equivalent problem. Okay? All right. So now this problem looks more like that problem, basically, but I still have greater than or equal to constraints here. So how can I get rid of these greater than or equal to constraints? Well, I want to turn them into less than or equal to constraints, right? Just like that one. So how can I achieve that? Just multiply both sides by -1, right? Okay. So if I do that, then I obtain the following. So I want to maximize Cx subject to ax less than or equal to b and minus ax less than or equal to minus b. So my LP problem in standard form is actually equivalent to the last problem that I wrote down, right? And nice thing is that that problem is exactly in this form, basically, right? Okay? And if an LP problem is in this form, I know what the dual looks like. Okay, so that's exactly what I'm going to make use of right now. So one thing you should be careful about here is that, so remember we're defining a multiplier for each constraint, right? So we have m constraints here, we have another m constraints here as well. Okay? So because we replaced every equality constraint by two inequality constraints, so as a result, number of constraints is twice the number of constraints over there, right? Okay? So I'm going to call the corresponding multipliers by w prime, and for the second one, I'm going to call it w double prime. Okay? And both w prime and w double prime are actually vectors. Okay, are m-dimensional vectors basically. All right, so what does a dual problem look like? Well, now I'm going to make use of that. So I'm going to multiply W by B. So which means that I'm going to multiply W prime by B and W double prime by minus B. And if I do that, what does the objective function look like? So I'm going to minimize W prime times B minus W double prime times B, basically, right? Is that clear? So I'm just taking the inner product of this with this and the inner product of this with this one. Okay? That defines my objective function. What about the constraints? So this is where you should be careful. I'm multiplying W with A. Okay? So my W consists of W prime and W double prime, and my A consists of A and minus A in this case. Okay? So basically, you can think of it this way. So I have my W prime followed by my W double prime, and my A matrix is given by A and minus A. Basically, right? Okay? So I'm going to take the inner product. Basically, what do I have? W prime times A minus A. Exactly. What about the right-hand side? E is going to be greater than or equal to C. And what's my C? Well, C is the same. Is greater than or equal to C. And then I want W prime to be greater than or equal to 0. And I want W double prime to be greater than or equal to 0 as well. So has everybody followed this part, basically, the constraint part? Okay? All right. So now I want to simplify the dual problem a little bit. So let me look at the objective function again. So I can write the objective function as follows. W prime minus W prime times B, basically, right? So that objective function is the same as this one, basically, right? Okay? And similarly, if I look at the constraints, I can write this as W prime minus W double prime times A is greater than or equal to C. And W prime is greater than or equal to 0. W double prime is equal to 0. Is greater than or equal to 0. Okay? So all I'm doing is I'm just sort of factoring B in the objective function and factoring the matrix A in the constraints, basically. Okay? Now, what's the advantage of doing this? Well, if I look at the objective function and the constraints, I always have W prime minus W prime and W prime minus W double prime, right? Okay? So as a result, what I'm going to do is I'm going to define a new variable and set it equal to this, basically. Okay? So let's define a new variable. I'm going to call it W. And W is exactly the difference of W prime and W double prime. So with this definition, then I can rewrite the objective function as follows. What's the new objective function now? So it's going to be just WB, basically, which is the same as that objective function. Okay? Subject to, what about the constraints? WA is greater than or equal to C, basically. Now, what about these conditions here? Well, so this is where you should be careful. So remember, W is the difference of two non-negative variables, right? Okay? And if you recall, so we said that whenever we have a free variable, we can always express it in terms of the difference of two non-negative variables. So here we're just doing it the other way around. Okay? So we have the difference of two non-negative variables. So what can I say about the sign of W? Well, the sign of W can be anything, basically, okay? It can be positive, it can be 0 or negative. So as a result, to signify that, I'm going to simply say that W is just a free variable, okay? Of course, W is a vector of variables, basically, okay? So as a result, W is just free. And this is the dual problem corresponding to that primal problem, okay? Now, let me compare this with the dual problem of that problem, basically. The objective function is the same, okay? The constraints are the same. The only difference is that W is no longer non-negative, unlike that example. Okay? Now, let me try to explain why this has to be true in general. Please pay attention, this is important. So remember, when we're driving the dual problem, we said that I have to multiply these constraints by non-negative numbers so that the inequality does not change direction, right? That was the reason why W has to be non-negative. Okay? Whereas right here, we actually have equality constraints. Okay? And if you have an equality constraint, you can multiply by any number that you want. Okay? And the equality will never be affected, basically. Okay? So as a result, basically, corresponding W values are no longer necessarily non-negative. They can be anything. Okay? Because whenever you have an equality constraint, you can multiply by any number that you want, positive, negative, 0, and the equality will still be satisfied. Okay? On the other hand, in this version of the problem, we wanted to preserve these inequalities, so as a result, we had to pick W's as non-negative numbers. Okay? So if I look at the standard form LP problem, the only difference is that I no longer have this restriction anymore. Okay? I still have the same objective function, same constraints, but W is now a free variable. Okay? Is that clear? Are you sure? Okay. So as a result, then if I change my constraints from less than or equal to equal to, the corresponding effect on W is it was non-negative over there, it becomes free over here. Okay? Once again, any questions? All right, so this is the first form that we're going to look at. All right, so now let me look at another form. So suppose that now my problem looks like the following. I want to maximize Cx subject to Ax less than or equal to b. But suppose now that x is a free variable. So it's almost the same as this one, except that we no longer have this non-negative restriction on x. Okay? So now my question is, how would the dual problem be affected in this case? Okay? So once again, we're going to first of all try to rewrite that problem so that it is going to look like this one. Okay? So I want to rewrite, I want to turn it into an equivalent LP problem, which would exactly look in this format, basically. Okay? So how would I achieve that? Well, the objective function is okay, the constraints are okay, the only problem is, basically, my variables are free, right? So I need non-negative variables. So how can I turn free variables into non-negative variables? Exactly. So I'm going to define two non-negative variables. I'm going to call it x prime and x double prime. And let x be given by the difference of these two. Okay? So now, if I write each free variable as the difference of two non-negative variables, then my problem will actually look like this one. Okay? So let's do that. So what does the objective function look like? So instead of x, I'm going to write x prime minus x double prime. So I have cx prime minus cx double prime. Subject to, what do the constraints look like? Is less than or equal to b. X prime is non-negative, and x double prime is non-negative as well. Those two problems are equivalent, basically, right? Okay? And secondly, if you look at the last problem, the second LP problem, that's exactly in the same form as this one. Right? Okay? So, which means that I can take the dual of this problem. So, this time I didn't change the number of constraints, right? So, I still have the same number of constraints. All right, so what does the dual problem look like? Well, let me start with the objective function. So, it's going to be a minimization problem. So, what's the objective function of the dual problem? So, it's going to be w times b, basically, right? Okay, so the objective function does not change. What about the constraints? Now, once again, you should be careful here. So, WA is greater than or equal to C, and W times minus A is greater than or equal to minus C. Okay? So, in other words, in this case, your A matrix looks like the following. So, I have my W, and my A matrix will be given by A followed by minus A. Okay, so this is my new A matrix. Okay, and my new C vector is given by C and minus C. Okay, so as a result, W times A is greater than or equal to C, and W times minus A is greater than or equal to minus C. Okay, so I have two constraints: WA is greater than or equal to C, and minus WA is greater than or equal to minus C. Another way of saying this is, remember, we're actually sort of defining constraints for each column. So these are the constraints corresponding to x prime, and these are the constraints corresponding to x double prime, basically. Okay? And then I want W to be greater than or equal to 0. Okay? Just like in that example. All right, so now I want to simplify the dual problem. Okay? So I have W times A is greater than or equal to C, minus WA is greater than or equal to minus C. First of all, I can multiply this by minus 1. So if multiplied by minus 1, what do I get? WA is less than or equal to C. Right? Here we have WA is greater than or equal to C. WA is less than or equal to C. Well, these two imply that WA is exactly equal to C, basically, right? Okay. So the dual problem looks like the following. I want to minimize WB subject to WA is exactly equal to C, and W is non-negative. Okay, so now what's the corresponding effect then? Well, if my decision variables in the primal problem are free, then the corresponding constraints are equality constraints. Okay, in the dual problem. Let me just go back to the previous example. I had equality constraints in the primal problem. I have free variables in the dual problem. Okay? So now, I have free variables in the primal problem. I have equality constraints in the dual problem. So do you see the symmetry between the two? Yes. Okay? So whenever I have free variables in one problem, the corresponding constraints are equality constraints, basically. Okay? And vice versa. Is that clear? So, has everyone followed how we obtain these constraints? Okay? I mean, all I'm doing is, so I'm looking at the columns corresponding to x prime. I'm looking at the columns corresponding to x double prime as well. So this is the first set of constraints. This is the second set of constraints. Okay? And then I'm just saying that, well, these two are equivalent to WA is equal to C, basically. Okay? Any questions again? All right, so I'm going to look at one other form. So suppose that the primal problem looks like the following. I want to maximize Cx subject to Ax less than or equal to b, but now x is less than or equal to 0. So I still have less than or equal to constraints, but my decision variables are non-positive now. Okay? So the question is, how would the dual problem be affected by this? Exactly. So first of all, just like we do, I'm going to turn this problem into exactly that form. Okay? So let us define x prime to be equal to minus x. And if I define x prime to be minus x, since x is non-positive, x prime will be non-negative, basically, right? So let me rewrite my problem in terms of my new decision variable. So it's going to be maximize minus cx prime, right? X is equal to minus x prime, basically. Subject to minus ax prime is less than or equal to b, and x prime is greater than or equal to 0. Okay? So these two problems are equivalent again. And furthermore, this problem is exactly in the same form as that problem, right? So now I can take the dual. So what does the dual problem look like? So what's the objective function? Well, the objective function is just WB, right? Okay. What about the constraints? So minus WA is greater than or equal to minus C. Right? And then W is greater than or equal to 0. Okay? All right, so now all I'm going to do is, what happens if I multiply these constraints by minus 1? So I have WA is less than or equal to C, basically, right? Over here. So the dual problem looks like minimize WB subject to WA is less than or equal to C, W is greater than or equal to 0. So once again, please pay attention. So in this example, X is non-negative. The corresponding constraints are greater than or equal to constraints in the dual, right? Now in this example, X is non-positive. The corresponding constraints are also less than or equal to. Okay? So as a result, if I change the sign of my variables in the primal problem, then I change the corresponding constraints in the dual problem. Okay? So if I have free variables, then I have equality constraints. If I have non-positive variables, then I have less than or equal to constraints. Okay? So as a result, hopefully you see the relationship between the sign of the primal variable and the type of the dual constraint. Okay? All right, there's one last form that I want to discuss. Sure.
The sign in the primal problem should be always smaller or equal to like AX. It always stays the same, AX smaller or equal to B. It doesn't change, right?
So the next example, now I'm going to change that. Okay? That's going to be the next example. Any other questions so far? All right. I can use this part. So suppose now that my primal problem looks like the following. I'm going to maximize Cx subject to Ax this time greater than or equal to B and X non-negative. So we already have none less than or equal to here. We looked at equality case in the first. So now suppose that the constraints, primal constraints, are greater than or equal to. Okay? So the question again is, how is the dual affected by this? Well, once again, first of all, I want to turn this constraint or turn this problem into this form. Okay? So how can I do that? I want to have less than or equal to constraints instead of greater than or equal to constraints. So how can I achieve this? Exactly. So multiply each constraint by -1, right? So let's do that. And if I do that, I have maximize Cx subject to minus Ax less than or equal to minus B. And X is not negative. So now my problem is exactly in this form. Okay? And I can compute the dual problem. So what's the objective function of the dual problem? So it's going to be minimize minus WB subject to, what are the constraints? Minus WA is greater than or equal to C, basically, right? So minus WA is greater than or equal to C, and W is non-negative. Okay? Now, one thing you should pay attention to here is the following. So if you look at the objective function and the constraints, you always have minus W here, right? So minus W and minus W. Okay? So what I'm going to do is I'm going to define a new variable, which I'm going to call W prime, and I'm going to set it equal to minus W. Okay? Just to get rid of that minus sign. So now my new dual problem looks like the following. So I want to minimize, instead of minus W, I'm going to write W prime. So W prime times B, subject to. So instead of, again, minus W, I'm going to write W prime. So W prime times A is greater than or equal to C. But since W is greater than or equal to 0, W prime will be less than or equal to 0, basically, right? So W prime will be less than or equal to 0. Okay? Now, in the primal problem, if I have less than or equal to constraints, in the dual problem, the corresponding variables are non-negative. Okay? Here, if I have greater than or equal to constraints, then the corresponding variables are non-positive now. Okay? So if I change the type of constraints in the primal problem, then that affects the sign of the dual variable in the dual problem. Okay? So, as a result, hopefully you start to see the relationship between the two problems. Okay? So, the type of the primal constraint affects the sign of the dual variable. Okay? And the sign of the primal variable affects the type of the dual constraint. Okay? So there's a relationship between the two. Let me repeat that again. The type of the constraint in the primal problem affects the sign of the dual variable. Okay? And the sign of the primal problem affects the type of the dual constraint. Okay? And actually we can summarize this in a table. And from this point on, you can just use this table to find the dual problem. So this is one of the most important tables in this course, okay? So I want to assume that the primal is a maximization problem, so that the dual will be a minimization problem. So in the primal problem, if the ith constraint is a less than or equal to constraint, okay, then the ith dual variable is non-negative. So for instance, here we have a less than or equal to constraint in the primal problem. This is the corresponding dual problem. The corresponding variable is non-negative. Okay? All right, so if the ith constraint is an less than or equal to constraint, greater than or equal to constraint rather, which is this form right here, the corresponding dual variable is non-positive. Okay? So the ith dual variable will be less than or equal to 0. Okay? And finally, if the ith primal constraint is an equality constraint, then what about the ith variable? Well, just like we did here, if we have an equality constraint, then the corresponding dual variable is free, basically, okay? So the ith variable is free. So these are the relationships between the type of the primal constraints and the sign of the dual variable. Okay, so now by the symmetry, there will also be a relationship between the sign of the primal variable and the type of the dual constraints. So let's write that. So just to use a different index, so suppose that the jth variable is non-negative in the primal. Okay? So if the jth variable is non-negative, then the corresponding dual constraint is also greater than or equal to constraint. Okay? So the jth constraint is greater than or equal to. If the jth variable in the primal problem is a less than or equal to constraint, is less than or equal to 0, which was the case over here. So if we have a less than or equal to constraint here, then the corresponding constraint is also less than or equal to constraint. Okay, in the dual. So the jth constraint is a less than or equal to constraint. And finally, if the jth variable is free, what about the jth constraint in the dual problem?
Equality.
It's an equality constraint, right? So if we have a free variable, then we have equality constraint in the dual problem, okay? So essentially, by using this table, you can figure out the dual problem for any given LP problem, right? Yes? This is a maximization problem. This is a minimization problem. Okay? So this is, if your problem is given in terms of minimization problem, then this will be your primal problem. So this will be the corresponding dual problem, right? So the roles of primal and dual can interchange, right? So if I give you a problem in terms of maximization problem, then this will be your primal problem, and this will be your dual problem. If I give you a minimization problem, then you can use this as the primal problem. So this will be your dual problem then. Yes? Exactly. Now I'm going to give you an example and we're going to stop. That point.
Non-negativity, Jet variable'da non-negatif'ti, constraint'de büyük eşittir.
Yes, yes.
Yukarıdaki aşağıdaki farklı olmuş.
Yes, but one is a maximization, the other is a minimization problem. So that's okay. So that's why you should be careful. So let me just give you an example, just to illustrate how you're going to use this table. So suppose that we have the following problem. I want to maximize 4x1 plus 2x2 plus 3x3 minus 5x4. Subject to 2x1 plus 3x2 minus x3 plus 6x4 is less than or equal to 10. x1 minus 3x2 plus x3 is greater than or equal to 8. And finally 6x1 plus 3x3 plus x4 is equal to 20. So x1 is greater than or equal to 0, x2 is, let's say, less than or equal to 0, x3 is greater than or equal to 0, and x4 is free. So now this is an LP problem with all sorts of different constraints and all sorts of different sign restrictions, okay? So what I want to do is I want to take the dual of this problem directly using this table, okay? I just want to illustrate how you're going to use this table, basically. So since the primal is a maximization problem, I'm going to use this as my primal problem, okay? So the dual problem will be given by a minimization problem. I have three constraints, so I need three dual variables, W1, W2, and W3. So the objective function is always equal to b times w. The objective function never changes. So I'm going to have 10 times w1 plus 8 times w2 plus 20 times w3. Okay? So that's the objective function. That never changes. Okay? Now, what does the first constraint look like? Well, for the first constraint of the dual, I'm going to look at the first column of the primal problem. Okay? So I have 2 times w1 plus 1 times w2 plus 6 times w3. Okay? Now, before I determine the type of constraint, the right-hand side value will be the objective function coefficient, which is 4. Okay? So now I'm going to try to determine the correct type. Okay? So what is the correct type of the constraint? Well, so this is the first constraint of the dual problem, right? So I'm going to look at the first constraint. Okay, so j is equal to 1. So I'm going to look at the corresponding jth variable in the primal problem. Okay, so I'm going to look at x1, and x1 is non-negative. So this tells me that if x1 is non-negative, then this constraint should also be greater than or equal to constraint. Okay, so as a result, the correct sign will be greater than or equal to. Okay, so now I'm going to look at the second constraint. So I'm going to look at the second column. So I have 3w1 minus 3w2. There is no w3. And the right-hand side of this constraint will be equal to 2. Okay? So now I want to figure out the type of the constraint. So I'm going to look at the second primal variable. The second variable is less than or equal to 0. So if the second variable is less than or equal to 0, then the second constraint in the dual problem will be less than or equal to constraint. Okay? So as a result, this will be less than or equal to. Okay? Then I'm going to look at the third column. So minus w1 plus w2 plus 3w3, and the right-hand side will be equal to 3. So now I'm going to look at the third variable, primal variable. So it's a greater than or equal to 0 variable. So if the third variable is not negative, then the third constraint is a greater than or equal to constraint. Okay? So as a result, the third constraint is also a greater than or equal to constraint. Finally, I'm going to look at the column of x4. So I have 6 times w1. There's no w2 plus w3, basically, right? So 6w1 plus w3. And what's the right-hand side value? Minus 5, basically, right? So that's the right-hand side value. Now, x4 is a free variable. Well, if I have a free variable in the primal problem, then the corresponding constraint is an equality constraint. Okay? So as a result, I'm going to have equality here. So far, I just used this part of the table, right? To determine the type of the constraints. So now I'm going to use the upper part of the table to determine the signs of my dual variables. Okay? So I'm going to start with the first dual variable. So the first dual variable corresponds to the first primal constraint. Okay? So the first primal constraint is a less than or equal to constraint. So the first constraint is less than or equal to constraint, which means that the first variable will be greater than or equal to 0. Okay, so W1 is greater than or equal to 0. What about W2? Well, W2 corresponds to second primal constraint, which is a greater than or equal to constraint. So if the second constraint is greater than or equal to, then the second dual variable is less than or equal to 0. Okay? So W2 will be less than or equal to 0. W3 corresponds to the third constraint. The third constraint is an equality constraint. Well, if third constraint is equality, then the third variable is a free variable, right? So W3 will be free. And this is precisely the dual of the problem. Okay? Now, let me just say one last thing before we quit. So, as an exercise at home, please do the following. Take the dual of this problem once again. Okay? Take the dual of this problem. Of course, now, since this is a minimization problem, you're going to use this as your primal problem. Okay? And then based on that, this will be your dual problem now. Okay? So, basically, the ith variable non-negative corresponds to this problem. The ith variable less than or equal to 0 corresponds to this problem. So if you just take the dual of this problem correctly, you're going to see that you get exactly the primal problem again. Okay? So let's stop here and we'll continue.